afternoon. I'm Nancy Neal-Jones from the Office of Communications at NASA's Goddard Space Flight Center in Greenbelt, Maryland. Today, we will reveal new and unexpected discoveries from NASA's OSIRIS-REx mission. Telecom graphics are available right now at https://svs.gsfc.nasa.gov/13154. I'll repeat, https://svs for Scientific Visualization Studio.gsfc for Goddard Space Flight Center .nasa.gov/13154. The Origin Spectral Interpretation Resource Identification Security-Regolith Explorer, OSIRIS-REx, spacecraft launched September 8, 2016, and began orbiting the asteroid Bennu on December 31, 2018. Since its arrival at Bennu, the spacecraft has been investigating the asteroid and searching for an ideal site for sample collection. To give more insight on the mission and new science results, today's briefing panelists include Coralie Glaze, Acting Director, NASA's Planetary Science Division, Washington; Dante, Lauretta, OSIRIS-REx Principal Investigator, University of Arizona, Tucson; Coralie Adam, OSIRIS-REx Flight Navigator, KinetX Inc. Space Navigation and Flight Dynamic, Simi Valley, California; Rich Burns, OSIRIS-REx Project Manager, NASA's Goddard Space Flight Center, Greenbelt, Maryland. We will now begin with Coralie. Coralie?
Thank you, Nancy. NASA's Planetary Science program actually runs several missions that are studying the small bodies that include asteroids throughout the solar system. We study these asteroids to learn more about the history of our solar system and our origins. The small bodies missions, both currently operating and planned for the future, will help the scientists start to answer questions like where did we come from, how did the major planets form, and how did Earth get its water. In its first 3 months, the OSIRIS-REx mission has already given us some amazing science to dig through, and I'm really excited about the results that are going to be presented here today. There are some unexpected results, some surprises, but this is an incredible team who can learn and adapt to achieve the ultimate goal of this mission, which is to collect a sample of the asteroid Bennu and bring it back to Earth. And so with that, I want to hand it over to Dante and jump right into some of these results.
Thank you, Coralie. This is an incredibly exciting time on the OSIRIS-REx mission. My first graphic shows a series of high-resolution images that were taken by our Polycam imager on board the spacecraft. These images were acquired on December 2nd of 2018, right as we were finishing the initial approach to the asteroid. And for most of the following months, they provided our best characterization of the asteroid surface. And they really demonstrate some of the surprises that this asteroid presented to us. First, unsurprisingly, because we had characterized the asteroid using ground-based radar astronomy, Bennu has an expected spinning top shape. It's roughly spherical with an equatorial ridge that seems to be dominated by its rotation and reflective of the fact that it's a pile of rubble or gravel and boulders loosely bound together by their own small gravity fields. However, we had expected from ground-based infrared and radio astronomy that the surface was relatively smooth and dominated by centimeter-scale particles, which are optimal for our touch-and-go sample acquisition mechanism, the device that will ultimately contact the surface of the asteroid to collect that material. In fact, we see a wide range of very large boulders on the surface. Our latest count is over 200 boulders larger than 10 meters in diameter. So there's something interesting going on with the asteroid geology. Not only do we see a lot of boulders, but we see that they have a very wide range of reflectivity, or what we call normal albedo. We're seeing things as dark as only reflecting about 3.5% of the light that's shining on the surface from the sun, up to over 20% reflectance in some of the brightest particles on the surface. As a sample scientist who's interested in getting this material back into our laboratories here on Earth, this is really exciting because it means that we're going to have a wide range of materials to study from the dawn of the solar system to understand the processes of planet formation and even why Earth is a habitable planet with abundant oceans and origin of life occurring here. However, it may pose some challenges for our navigation systems, which rely on LiDAR instruments, which are lasers that reflect off the surface to give us a range to the asteroid, as well as image-based technologies to guide us into the potential sample site. We show this movie with the asteroid rotating. One of the most interesting discoveries so far is that since we've been watching the asteroid astronomically beginning in 1999 up into observations in 2018, we've seen the rotation rate of Bennu increasing. Because of the latest observations, we can attribute this to a known phenomenon called the YORP effect, which is basically how interaction with sunlight causes the asteroid rotation rate to increase. And probably the most easily understandable way to characterize this is what we call the YORP doubling time. In about 1.5 million years, we predict that Bennu will be spinning at twice its current rate, so we definitely see the asteroid spinning faster and faster. We have learned a lot about the composition of Bennu from our initial observations, and we have 3 instruments that allow us to determine the minerals that are on its surface. We have a thermal emission spectrometer called OSIRIS, which goes out to very long infrared wavelengths, capturing the heat that's coming off, but also containing information about the minerals on the surface. We have a visible and near-infrared spectrometer called OSIRIS, which characterizes the way sunlight is reflected off and gives us additional indications about the minerals on the surface. And then we have our mapping camera, the MapCam, which has color filters that allow us to look at very broad variations in reflectance in visible wavelength ranges. We have learned that Bennu is dominated by water-rich clay minerals or phyllosilicate minerals, which is very exciting and allows us to really go after the kind of material from the early solar system that we're interested in. But with the MapCam, we've been able to get resolved images, and in the graphic number 2, I'm showing you in the middle there different colors from our approach phase with the MapCam, and then over there on the right, on the top, we've got the ratios of those different colors, and this matches a known mineral called magnetite, or iron oxide, or more familiar on Earth, sometimes called a lodestone. Magnetite is very interesting because it also forms in aqueous systems, often as a result of very intense action of liquid water. So this confirms Bennu as the ideal choice for our sample return target. On graphic 3, I reveal probably the biggest surprise of the early phases of the OSIRIS-REx mission, and I would say one of the biggest surprises of my scientific career. When we got into orbit, our first orbital phase A, we actually were expecting that to be a time for the science team to kind of process the information that had already been acquired, and for the flight dynamics team to learn how to operate the spacecraft in close proximity to the asteroid. But what I'm showing you here are actually a composite of 2 different images from the navigation camera. There's a short exposure image, which is showing you the asteroid surface in the lower left, and then a long exposure image, and if you look just off the limb towards the center of the image, you'll see a whole series of bright pixels. Those are, in fact, particles that are ejecting off the surface at relatively high velocity. So Bennu is part of a category, a very small group of small bodies in the solar system called active asteroids. We are seeing Bennu regularly eject material into outer space. We saw the first event occur on January 6th of this year, and then we instituted a more rigorous monitoring process using the navigation camera starting on January 11th, and we're able to continue that high cadence of observations through February 18th. And we have seen about 11 such events over that time period. More are being discovered as we get better at analyzing and processing the data and extracting small signals from that information. 3 of those events have been substantial, with dozens or over 100 particles being ejected clearly into the asteroid environment. The particles seem to be in the size ranges of centimeters up to tens of centimeters in diameter, and they're moving with velocities of centimeters per second, which is very slow relative to the asteroid's acceleration and escape velocity, up to several meters per second, which means they're clearly being ejected into interplanetary space and away from the asteroid. Some of those slow-moving particles have been observed over periods of at least a week, and they appear to be trapped in the asteroid's gravity field and are ending up in orbit around Bennu. So they're creating its own set of natural satellites. And then some of them have been observed to fall back onto the surface. Basically, it looks like Bennu has a continuous population of particles raining down on it from discrete ejection events across its surface. This is incredibly exciting. We don't know the mechanism that is causing this right now. In fact, we're still learning how to process the data, analyze the information, and make sense of what's going on at this asteroid. And then in my final graphic, graphic number 4, it's just an example of one of our highest resolution images acquired to date. This is a shot from our Polycam taken from the first detailed survey station, and it shows the general rugged nature of the asteroid surface. The field of view here is 70 meters. The good news, and the reason I picked this image to show you, is that at smaller scales, we are seeing patches of fine-grained regolith, which is exactly the kind of material that we expect to be able to collect with our TAG-SAM sampling device. So even though the surface overall looks bouldery and rugged and rocky and really not what we expected from our ground-based astronomy, we are honing in on areas of sample material, and those will be obvious areas of interest as we move forward with the mission. So I'm going to hand it over to Coralie Adam. Coralie is the optical navigation lead for the mission, and she has been responsible for a large amount of the success of our operation so far. So Coralie?
Thank you, Dante. Moving on my first graphic, on December 31st, the navigation team delivered OSIRIS-REx into a record orbit around Bennu, making Bennu the smallest planetary body to ever be orbited by a spacecraft. The team achieved another record for the smallest orbit around a planetary body, which is an elliptical orbit with the closest distance falling just under a mile from the asteroid center. Getting into this orbit around such a small asteroid is really challenging, given the fact that the force of the radiation pressure or the sunlight acting on the spacecraft is on the same order of magnitude as the gravitational pull from Bennu. On the left-hand side of this graphic, you see the orbit as if you're looking down from the sun, and on the right-hand side, you see a side view. You can see that the orbit plane is facing the sun. We call this a frozen orbit because it uniquely balances forces between the solar radiation pressure and gravity, so it allows for a more longer-term stability. When we got into this orbit, it was so stable that we didn't need to do any adjustments during the scheduled 8 weeks in orbit. Moving on to slide 2. The objective of this initial orbit phase was to transition to a method of navigation called landmark tracking, which would improve our navigation performance for future mission phases. Instead of finding the geometric centroid of Bennu, which you can see on the left-hand side of the graphic, we now navigate by surface features, which have allowed us to better understand characteristics of both Bennu and the spacecraft that affect the navigation performance. Now, what's really impressive about the outcome of our time in orbit is that we have demonstrated meter-level navigation accuracy, which is even better than the Earth-based GPS on your smartphone. You can see in these two NavCam views from orbit, and as Dante mentioned, that Bennu is very dense with boulders, which will make for a more challenging sample collection. Luckily, our predicted navigation performance has been 10 times better than what we expected before we arrived at Bennu, which means we will be able to tighten down our analyses and target a more precise bullseye tag. Moving on to slide 3. Now, just 6 days after we got into orbit, we've observed our first particle event. And this discovery was only observed because of our optical navigation method of taking long exposure images of stars, which help refine our precise measurements. So given this image-based and dynamical nature of this phenomenon, our navigation team has been able to quickly build up a tool set to characterize the behaviors of these particles. So work is underway to use these sparse data of just a few images of pixels emitting from the asteroid to trace these particles back to the surface, as well as predict where they are heading. So with that, I will close by giving big kudos to all the hardworking members of the navigation team and our entire mission team who have really demonstrated amazing and unprecedented capability on this mission so far. So I'll hand the floor over to Rich Burns, who will further speak to this graphic before moving on.
Thanks very much, Coralie. So as Coralie mentioned, we were only 6 days in orbit, of the smallest orbit ever around a planetary body when we observed this event. You can imagine we were modestly concerned about particles being ejected from the surface of the asteroid unexpectedly. And so that prompted us to do a quick turnaround safety assessment. In other words, how likely was the spacecraft to be impacted by these particles? Were we safe in orbit? We did that very quickly within a day using the available information we had and techniques that we were familiar with for low Earth orbit collision avoidance calculations. These calculations we did with 3 independent parties and all came up with similar results showing that we had very low likelihood of seeing an impact resulting from one of these particles. Safety analysis was further refined and informed by subsequent observations. Dante mentioned the 11 events that we've seen. 3 of them have been major, like this one you see on this graphic. All of that information led us to the conclusion that the spacecraft was safe in orbit, and we persisted there to observe these events as the orbital environment was the optimal for such observations. If we could move on to my first graphic, please. So what you see here is another high-resolution image of a location on the asteroid with an overlay of a circular region we're calling the original target area. This is the accuracy with which OSIRIS-REx was designed to touch the asteroid to collect the sample. So we were looking originally for a 25-meter radius hazard-free zone. You can see from this image, this isn't it. And the asteroid is so rugged that there is unlikely to be any 25-meter radius hazard-free zones. What do I mean by hazards? Those big boulders represent hazards, as do tilts, severe tilts on the surface and slopes on the surface of the asteroids. You do see in the upper left-hand corner a region of small-grained samples, which may be appropriate for a sample collection. Of course, that area is much smaller than the area outlined in white here, the 25-meter radius circle. However, our system performance, as has been noted by both Dante and Coralie, has been extraordinary to date. Our spacecraft, built by Lockheed Martin, has performed maneuvers with very high levels of accuracy and precision, allowing us to do things like stay in orbit without trim maneuvers, as Coralie mentioned. Our navigation performance has been exquisite. The modeling that the navigation team, collaborating with Goddard and KinetX, both collaborating, has been extraordinary. And the level of modeling, the fidelity of the modeling of things like solar radiation pressure and re-radiation from the spacecraft has been extraordinary. So we feel confident that our systems and our teams are up to the task of tagging to a sample collection site of much smaller area than was previously envisioned. That's what gives us confidence to move forward with what we're calling bullseye tag. So bullseye tag, you can imagine you're just shooting at a dartboard, just trying to hit the board. Well, now we're going to try to hit the center of the bullseye. We feel like the performance of the system and the team supports that notion, and we are working actively to make it happen. Next graphic, please. What you see on the next graphic is just an animation of our tag sequence. So the spacecraft will leave orbit, and you'll see a deployment of the TAG-SAM arm with the TAG-SAM head featured in that deployment. The spacecraft will make 2 maneuvers to descend to the surface of the asteroid, and we will not land on the asteroid. The spacecraft will touch the asteroid with the head, the sample head, hopefully on a level spot, and we will expel pressurized nitrogen gas to disturb the regolith. That regolith will be collected within the sample head itself, which looks like an air filter, more or less. That fine-grained sample will be collected there and will back away from the asteroid. And then once we're away from the asteroid, we have some techniques that we'll use to measure the size of the sample that we got, and then we'll stow that sample in our sample return capsule. With all that said, I'm going to turn it back over to Dante and let him close things out.
So just to summarize, first of all, the OSIRIS-REx team continues to perform at an amazing level of professionalism and precision, and it's an honor to be the leader of this program. I couldn't be more proud of everything that's been accomplished so far, and because of that, it gives me great confidence that we're going to be able to target a bullseye tag event for summer of 2020 and get that precious sample for a stow and return back to Earth. Bennu has turned out to be an ideal target from a compositional perspective. We are seeing abundant water-bearing minerals on the surface, and through the magnetite detection, inference of intense aqueous activity in the past history of this asteroid. It does present us challenge. It's a more rugged surface than we had predicted from our ground-based astronomy, but we feel like there are patches of fine-grained material on the surface that we can collect with the TAG-SAM device. And of course, as I hope Coralie has convinced you, the flight dynamics and navigation team is absolutely the best in the world. Their cutting-edge astrodynamics techniques are not only going to make sure the spacecraft remains safe, but also that we collect all the scientific data we need to make the best sample site selection decision possible and ultimately guide us down to get that material off the surface. And then almost more impressively, we have such a tight coupling between the science and engineering groups on this program that they are also making a major contribution to characterizing these particle ejection events, and the tools and procedures and analysis capabilities that they bring to the team are going to end up producing some of the greatest scientific discoveries. Definitely not what we expected to see at the asteroid, but an excellent opportunity for us to understand active asteroids, volatile ejection and loss from these bodies, and overall the distribution of this kind of material in the solar system, and ultimately its pathway to delivery to the surface of the Earth. So thanks to everybody on the team for their hard work to date, and buckle up, the best times are ahead of us, and it's going to be a great ride.
Okay, thank you, Dante. Operator, we're now ready to take questions from the media. Please state your name and affiliation. Operator?
Thank you. At this time, we will begin the question and answer session. If you'd like to ask a question, please press star 1, unmute your phone, and record your name when prompted. To withdraw your question, please press star 2. One moment, please, for the first question. Ivan Caron, your line is open.
Thank you. In terms of probability, how much more risky do you expect the sampling operation to be because of what you found out?
So this is Rich. I can take that one. We don't have a quantification of that yet because we are still in the process of mapping the asteroid to identify the candidate sample sites. So we're going to make a site selection in the summer months, and at that point we'll have a better idea of the area of the sample site relative to our previous requirements.
And will this delay at all the sampling compared to what you forecast initially, July 2020 or after?
No, the answer is no.
Okay, thank you.
Our next question comes from Marina Karen. Your line is open.
Hi, this is a question for Dante. You said you don't know for sure what's causing these ejections, but do you have any ideas based on the study of other active asteroids? And did you expect to see this kind of activity on Bennu? Why or why not?
Thank you for that. That's a great question. We certainly did not expect to see this activity because there's so few asteroids that are known to be active. There's about a dozen of them of the 800,000 asteroids that we know in the solar system. So the probability that Bennu would be active we thought was very, very low. That said, we did plan for such an event because we thought it might be possible, and we're very thorough in how we design the mission and how we approach the risk and safety assessments and also take advantage of scientific opportunities. So we actually do have requirements on the mission to look for dust and gas plumes, and we also have requirements to search for and characterize any natural satellites that may be in bound orbits around the asteroid. We did not expect that there would be ejections of particles that were creating natural satellites. That has never been seen before in any solar system object in history, so that's really exciting and a great opportunity for us to learn more about not only the surface of the asteroid, but also its gravity field. These are natural gravity probes, and they're orbiting very close to the asteroid, so we'll be able to get a great understanding of the gravity field and therefore the internal structure of the asteroid. We do have some mechanisms that are under evaluation. One of the very first things I did was we rallied the science team together. We made up a big list of all the possible things that could eject particles from the surface. It's a long list. There's a very creative team, and lots of ideas are out there. So my focus right now is full characterization of what has happened. As I mentioned, we have a great data set that goes from January 11th to February 18th, and we're still developing software and analysis tools to really understand what's in that information. And my first objective, which is underway, is to compile a table of the constraints. Basically, what do we know about the size of the particles, the energy of the events, the frequency, the composition, the source regions, et cetera. And once I have all of that information compiled, then we'll start to go through our different possible mechanisms and evaluate which one we think is the most likely.
Thank you.
Thank you. Our next question comes from Mark Gotch. Your line is open.
Yes, good afternoon, ladies and gentlemen. First off, congratulations on the incredible achievements you've made by already making the long journey to the asteroid Bennu. In talking about the discharges of particles, are these actually storms or small ejections of particles? Are you now looking at this, seeing this as looking at your bullseye collection location as it being something that you might have to wait through a long period of these type of particle injections or storms? Can you answer that?
Sure. Absolutely, we're trying to understand the nature of the ejection events. A couple of things that we do know is that they are discrete events. They happen near instantaneously, and whenever we see a large number of particles leaving the surface of the asteroid, they seem to be coming from a single location. We are still working to determine the exact locations of all the events that have been observed to date, and I think Coralie can probably tell us a little bit more because it's the flight dynamics tools and analyses that are helping us constrain those. And we're also trying to understand what might be the driving forces. We did go through perihelion on January 10th, so that was just 4 days after the first event was observed. But as we said earlier, that was only 1 week after we got into orbit when these things were really observable. So we don't know if it's in fact related to our closest approach to the sun. And Bennu's orbit is pretty eccentric. It goes from about 0.89 astronomical units at the closest approach to the sun or perihelion out to 1.35 AU at aphelion, or its farthest point from the sun. So there was a speculation that this might be related to the close approach, but we haven't confirmed that yet. We have seen the events continuing into the late February timeframe, and we're not seeing them, but we also have left orbit and we're much farther away from the asteroid, so they're not as observable as they were before. So all of these are open questions. It's one of the greatest things about being a scientist is you get to go chase down your theories and collect more data to understand them. But Bennu is really teasing us with this. I think it's really every time we think we understand what's going on, a new manifestation occurs, and we go back to the drawing board and start thinking over it again. So we're super excited, but we're also being very diligent and careful as we process the data. And Coralie, why don't you talk a little bit about the work you're doing to actually locate the ejection sites on the surface? Sure.
Well, what's challenging is that we have these, 2D images of particles, and we what's challenging is we are trying to link these particles from one image to the next, and then back out. We can measure things in the image plane in 2D space, the position and movement of the particles. And what we're focusing on is trying to make some good assumptions about how to project those 2D measurements into 3D space so that we can measure the 3D velocities, the cone or shape of the ejection, and traced the particles back to an origin site on the surface, as well as predict their orbits, suborbits, or hyperbolic escape trajectories from there.
Thank you very much. You are learning quite a bit. Thank you.
Thank you. Our next question comes from Malcolm Ritter, Associated Press. Your line is open.
Thank you very much. I have what I hope is a simple question. You talk about recovering the sample that you want to recover and bring back to Earth. You talk about this being pieces of regolith of below a certain size, and my audience has no idea what we're talking about. Are we talking about dirt or gravel or pebbles, or what is kind of an everyday English word that would describe the stuff you're going to collect?
Sure, I'll take that. This is Dante. So regolith is the term that we use to describe a loose blanket of rock and gravel, usually on the surface of an airless body. So we talk about the regolith on the moon or on Mercury and on asteroids. So basically what we're seeing, Bennu being a rubble pile, we've got boulders as large as 80 meters, and we are seeing particles right now down to a few centimeters, basically limited by the resolution of the images we've acquired to date. So in a sense, all of that would be considered regolith because we don't have bedrock or the solid material that makes up the bulk of the asteroid. For OSIRIS-REx specifically, we're looking for fine particulate regolith, and that's driven by the capability of the sample collector, which can pick up particles about 2 centimeters in diameter and smaller. So we're looking for the fine regolith that is capable of being ingested by the sampling mechanism.
So from what you say, I think 2 centimeters in diameter, that's what, 0.8 of an inch. So we're basically looking at gravel and dirt. I mean, is that a fair way to?
Yeah, gravel and silt or sand-sized particles. If we're looking at the geologic scale, so absolutely.
Yeah, so gravel and smaller then.
Right.
Yeah. Okay. And again, I'm struck, Dante, that in your paper, you were a first author in a paper in Nature that just went live, saying that the unexpected small size of safe collection sites. You said the sampling of which poses a substantial challenge to mission success, and yet here you sound like it's going to be a breeze, not a problem. So I'm kind of struck by, how confident are you can really pull this off?
Sure, and I would say everything we're doing is a substantial challenge, and so we shouldn't diminish the enormous amount of effort that it takes to make something like this happen. So, NASA has a long history of doing very difficult things and making them look easy, and that is continuing on with the OSIRIS-REx mission. And it is not trivial to deliver a spacecraft with meter-scale resolution to the surface of an asteroid in a microgravity environment, and we take that challenge very seriously. And the challenge got a lot harder when we saw the true nature of Bennu's surface. But I am confident that this team is up to that substantial challenge and that we will ultimately develop this bullseye tag capability and be able to successfully collect the sample from the surface.
Okay. Very good. Thank you.
Our next question comes from Doyle Rice, USA Today. Your line is open.
Good afternoon. Thanks for doing this. Very interesting stuff. Just a couple of quick questions for you, just kind of on a bigger term scale here. There's no anything that you've discovered today or announcing doesn't really have any specific impact on whether or not this particular asteroid will come closer or farther away to Earth over the next few hundred years. It's not really. This doesn't really leap out as a major discovery for whether or not it's going to potentially come close to the Earth. Looking at the British tabloids today, they all say that it's about ready to hit or some crazy thing, and I just wondered what your overall perspective is on that.
Well, one of the words in the acronym OSIRIS-REx is security, and Bennu is known as a potentially hazardous asteroid. So one of our objectives is to really understand the likelihood that Bennu is going to impact the Earth. We have done a lot of that work even pre-launch with our extensive astronomical campaign, and we have given an assessment of about a 1 in 2,700 chance of an impact late in the 22nd century. We haven't learned anything that would cause us to change that estimate of Bennu itself impacting. But I will say one of the fun and exciting offshoots of the particles is we do see these things leaving the vicinity of the asteroid. And so we think there's a reasonable probability that there might actually be a meteor shower associated with Bennu, and small particles might be coming in the sky. And so that would happen in late September every year, and it would be dominantly occurring in the southern hemisphere. So we're working with our colleagues at the SETI Institute in California to set up some monitoring cameras and actually see if there is a Bennu's meteor shower in September every year. And that'll help us with the science understanding these particle events, because it'll give us a much longer timeline about how frequently and how energetic and how many particles may have been coming off over thousands of years of Bennu history.
Okay, thank you.
The line is now open. Kenneth Chang, New York Times.
Yes.
Your line is open.
Thank you. My question is, Ryugu, the asteroid that the Hayabusa 2 mission is at, it also turned out to be this spinning top with a ridge and lots of boulders that turned out to be much more difficult to examine than initially anticipated. I was wondering, does this tell you something about the formation process of these rubble piles?
That's a great question, Kenneth, and absolutely, having two spacecraft at two of these objects gives us an enormous opportunity to advance our understanding of the field. And I would say already a lot of our ideas for how the spinning top shape formed are not being supported by the data that we've collected so far. For example, one of the things we reported in the Nature papers and also at the Lunar and Planetary Science Conference today is that there's a large number of impact craters on the equatorial ridge of Bennu, which makes it look like the surface is 100 million to maybe 1 billion years old, which implies that the spinning top shape in that equatorial region formed very early on in Bennu's history. And we had thought that this was actually related to what we call the Yorp effect that I referred to during the briefing, where interaction with sunlight and re-radiation of that energy as heat is causing the asteroid to spin faster and faster. And we thought that was the driving mechanism for production of the spinning top shapes. So we don't know the answer right now. You can imagine the science teams are really busy characterizing the data and really refining those theories. And we are planning a workshop in November, both sponsored by Hayabusa 2 and OSIRIS-REx, coming together to evaluate exactly that question. What have we learned from these two great missions, and what is that going to tell us about the formation of spinning top asteroids? And then overall, I would like to acknowledge the great collaboration that we have with our colleagues at JAXA and the whole Hayabusa 2 team. It's a really great relationship, and they have successfully sampled from the surface of Ryugu. And in fact, I'm leading a contingent of OSIRIS-REx team members next month in April to visit them and get lessons learned about how we can improve the chances of success for OSIRIS-REx sampling.
Our next question comes from Jason Davis, the Planetary Society. Your line is open.
Hi, thanks for doing this. Just had a question about, you said this was an active asteroid, and I was wondering if you could just clarify a little bit more about what that means when you say that. Is it that the interior is shifting around somehow in these dozen or so that you've seen before? And also, could you clarify, has this ever been seen before by any spacecraft, this type of particle ejection from an asteroid, or theorized to exist in this type of asteroid? Thanks.
Yeah, hi, Jason. Thanks for that question. So active asteroids were first discovered about 15 years ago when observers were looking at asteroids in the main belt that clearly had orbits that placed them well within that family of small bodies. And then they saw that they were developing an extended coma, very much like comets do. And so the original term that was used was main belt comets, where we had objects in the main belt. They looked dynamically exactly like every other asteroid that's out there, yet they were showing periodic activity. And examples of this are El Pizarro is one of the first ones that was discovered. There have been roughly a dozen of them that have been identified since then. Almost all of them are main belt asteroids, and they have shown a correlation with perihelion, although that correlation is not perfect. And the thinking was that these were probably icy bodies, that something happened, an impact had occurred on the surface, and subsurface ice had been exposed and recently, and then was now just going through cometary activity for a brief period of time. Other asteroids were seen to be undergoing the rotational acceleration via the Yorp effect, like we see on Bennu. And some of that, if you take that to the extreme case, the rubble pile of asteroids will actually fly apart because the angular momentum that's been added to the surface overcomes any cohesive forces that are actually holding the body together, including its own self-gravity. So it is a class of asteroids that have been observed. It's a very small number of them, and we think probably multiple things are happening. You could imagine the cometary kind of activity, the Yorp spin-up, or an impact. Basically anything that causes an asteroid to develop a coma of fine particles around it would label it an active asteroid. But we have certainly never seen anything like this from a spacecraft before. You know, we looked at the Eros and Itokawa data, and we talked to our friends on Hayabusa 2, and they're looking around asteroid Ryugu. None of those missions have ever detected active particle ejection from an asteroid surface before. So it's a really exciting opportunity to be able to characterize and understand the phenomena and decide if it is related to what's happening on other active asteroids or it's a completely unique occurrence. One thing that makes Bennu very different is you wouldn't see this from ground-based telescopes. It's not a massive amount of dust that would show up as an extended coma when you're looking at it like a comet.
Thank you. Our next question comes from Chen Sterone, New York Times.
Hi, thanks so much for taking the call. I was wondering, one of the Nature papers says that we think that Bennu's surface has changed over the last million years. Do we understand why and what process might be creating that change?
Thank you. That's also a great question. And it looks like there's several processes that are going on Bennu's surface right now. One of the things might be related to this rotational acceleration. So you can imagine Bennu is spinning faster and faster. And as the rotation rate increases, you add angular momentum to the surface, and that can trigger what we would call like a landslide or a mass wasting event, moving material downslope, filling in low-lying regions of the asteroid. We do see evidence of that happening on the surface. It does look like large amounts of material have moved on the surface and are moving down from the polar regions towards the equatorial areas. So we have active geology going on the surface. The other thing that we're seeing are these particle events, and some of the material is completely leaving the asteroid, but a lot of it is actually falling back onto the surface. And we've only been watching it for a few weeks, and this might have been going on for thousands or hundreds of thousands of years. So we're still trying to understand what kind of resurfacing might have taken place as a result of these particle ejection and fallback events on the surface.
Interesting. And do you happen to know if the fast spin period that lasted helped create the spinning top shape? Or might this activity be creating that?
I would say we thought before we arrived that it would be an increase in rotation rate that would lead to the spinning top shape. That was the leading theory going into the encounter with the asteroid. But as with all things, once you get there and you start studying the object itself, you know, that idea starts to get questionable. And the real reason we're questioning that model is because of these large impact craters, which are all over the equator of the asteroid. And it would take a long time. We estimate at least 100 million years to 1 billion years in the main asteroid belt to produce that crater population. So the rotational acceleration has got to be a relatively new phenomenon, because it's so large that if it, Bennu would have had to almost be not rotating at all even 8 million years ago to see what we're seeing right now. It probably started when Bennu shifted from the main asteroid belt into the near-Earth population. So again, this is why we explore. We've learned something surprising, and it's making us reevaluate our understanding of the basic formation mechanism of spinning top asteroids. And we're still sharpening our pencils and really collecting the data before we start to zero in on what we think the answer is.
Thank you. Our next question comes from Rick Lovett, freelance. Your line is open.
Thank you. Yes, I have. Can you give me the velocity range of the particles being ejected, and why don't they all either eject into interplanetary space or fall back? Because it seems like you're basically firing bullets out of the surface. How do they wind up in orbit?
Right, so we are seeing velocities of the particles from just a few centimeters per second up to about 3 meters per second in the fastest moving particles. And you're seeing a whole range of velocities there. And again, remember, we're still in the process of developing the tools and refining those numbers, and the work that Coralie and her team are doing are really contributing substantially to that. And so we're seeing, in some cases, hundreds of particles that are being ejected in a single event. And you're going to have a range of velocities. Some of them are moving so fast they leave the asteroid. Some of them are moving so slow they basically go up and right back down to the surface. And then some of them are in the sweet spot where they just happen to have the right velocity in the right direction to be injected into orbit around the asteroid. And we're still trying to understand how long those orbits are lasting. We have seen at least one particle that orbited for about a week, and then it did fall back down onto the surface. And we're evaluating other groupings of detections to see if there's any long-lived orbits. We do know that it's possible through our amazing radio science team. They've done an analysis of stabilities of orbits, and there are orbits that could last months or years. They're in very special locations, so it would just be fortuitous if a particle got injected right into that regime where it lasted for a long time. So my prediction right now, and just as a reminder, this is new, not even a month old in some cases, data, and we're still trying to figure out what's going on, is that most of these are going to be short-lived satellites, weeks to months, and end up re-impacting the surface.
Okay. Thank you. One other question, this is basically for NASA. Where are the images going to be located online? When I went to that website, all I got was the press release.
So you're asking about early release images? I mean, ultimately, the images will be stored in the Planetary data system along with all the rest of our archived data from the Planetary Science Division.
I'm meaning the ones that were being discussed today. Will we be able to look at them?
So we released one image of one of the biggest particle events, and those will be on the asteroidmission.org website. And then we are compiling all of the information and preparing for publication, and I'd like to say that's happening sooner rather than later, but it's a big effort with a big team and a lot of people working, and we want to make sure we get it right, and then when that publication comes out, all of the data that went into the analysis will be available as well.
Okay, thank you.
Thank you. Our next question comes from Emily Conover, Science News Magazine.
Hi. So I'm not sure if I missed this, but I was wondering, so for the particles that are orbiting, how high off of the surface of asteroid are these things orbiting?
Thank you. Again, we're still evaluating all of the orbits. We certainly have a lot more detections than orbital solutions at this point, and it's a tricky problem because not only are we dealing with the gravity from the asteroid, which is very small, but because of that, the radiation pressure from sunlight and even thermal radiation from the asteroid and from the particle itself end up influencing its trajectory. Really, I've only seen 4 orbital solutions coming from the team so far, and maybe Coralie wants to comment on this as well. Most of those have been at very low altitudes within the range of 100 to 300 meters from the surface. We had one that actually got up to about 1.2 kilometers from the surface, right around the range that the OSIRIS-REx spacecraft was orbiting. And so that's kind of the bounds that we have so far. But again, there's a lot more data than we've been able to obtain orbital solutions for. And maybe Coralie, do you want to speak to how we're going about orbit determination on the particles?
It takes identifying particles, associating them with each other from image to image. So we're developing software tool sets to still have a human in the loop, but to make it easier to identify and track those initial, some of the initial particle ejection events, and then once they get an initial kind of prediction for where they were going, then we go look in more images into the future and see if we can observe, detect more observations of these particles to refine their orbits. So work is underway to build up this tool set, and we've studied a few particles so far.
Our next question comes from Kimberly Cartier, EOS.org. Your line is open.
Hi, thank you for taking my question. You spoke about the composition of Bennu being phyllosilicates and other clay minerals. How similar is this to some meteorites that we've seen fall to Earth or other asteroids we've measured in space?
Thank you. That's a great question, and I can say that we are seeing nice correlations between the spectral characteristics of Bennu, both from the OSIRIS visible and infrared instrument and from the OTIS thermal emission spectrometer. And they look a lot like the rarest, most fragile, friable meteorites in our collections. These are special types of carbonaceous chondrites, and we use letters to designate them, and they look a lot like the CM chondrites, which are related to a big event in Australia where we have most of that material in 1969 in Murchison. And so we're optimistic that we have material similar in mineralogy to what we've seen in those very organic-rich and water-rich meteorites. I will say I'm a meteorite scientist by training and background, and when I look at the rocks on the surface of Bennu, they don't look like those meteorites do in hand samples, so there's definitely other things going on there. It's very exciting from that perspective. So, and we're also seeing things at meters and tens of meter scales, and we never had meteorites in our collections that look like that. So I would say spectrally and mineralogically, they look like they match those rare carbonaceous chondrites, but the nature of the boulders are suggesting there's more to the story than what we know from our meteorite samples so far.
Thank you.
Ken Kramer, Space Up Close, your line is open.
Hi, thanks for taking my question and for doing this. My question is about the compositions, actually. I wanted to know what do you know about the composition of the ejector particles? About the phyllosilicates, did you expect to see that on the surface or not? And have you seen any carbon compounds at all?
Thank you. Those are all great questions. So I'll start with what we have seen, which are both the phyllosilicates and the iron oxides. And those are not unexpected. Those were actually kind of the minerals we were hoping to see, water-rich materials, basically indicating that sometime in the ancient past, probably very soon after the solar system formed, in a much larger asteroid, which we think was Bennu's parent, there was icy material and rocky material that got a little bit heated up, and the water reacted and formed those clay minerals. We haven't detected the carbon-bearing compounds, the organic molecules, yet. We do expect that they're there just by similarity with the carbonaceous chondrite meteorites. Whenever we have those water-rich clay minerals, they're associated with organic material. And we think one of the reasons we haven't been able to detect them is the wavelength range where those spectral signatures occur are at longer wavelengths. More heat that's coming off the asteroid would make it harder to detect that signal. The good news is the asteroid's getting farther away from the sun. The surface is going to be cooling off. And by the time we get to the mapping station that's optimized for the detection of organics, we expect that the amount of interference from the thermal radiation from the surface will decrease. And then on to your question about the particle composition. We're looking at particles that are centimeter to tens of centimeters in size, and there hasn't been an opportunity to get the spectrometers on those to see if we can detect them. And that's going to be a challenging observation because the particles occur unexpectedly. We can't predict when they're going to eject from the surface. And we can't just be scanning all the time in the space around the asteroid in hope of catching one. So it will be fortuitous if we actually make a measurement that has particles in the spectrometer fields of view. But that doesn't mean we're not going to try. In one of the survey stations that are coming up in a few months, is optimized for looking at plumes and particles being ejected from the surface. We basically get behind the asteroid, so we're looking at the night side, and the limb will be illuminated by the sun, which will be on the opposite side of the asteroid. So if there's dust or gas, that'll be really well seen with the cameras because the light will be scattered and they'll really show up with a nice strong signal. And we'll also have the spectrometers on to try to characterize the plume events in that instance.
Thanks.
There will be no further questions.
Thank you for participating and have a great day. This concludes today's briefing.